Hi everybody. In this video we're going to show that if we have two sequences, an A and a B, and we know that those two sequences converge, then if we define a new sequence, A plus B, obtained by just adding corresponding terms in the two sequences, then not only will it be a convergent sequence, but it will converge to K plus L, right? The sum of the original two limits. So to prove this, we're going to go right to the definition. Say, what does it mean for A to converge to K? What does it mean for B to converge to L? So for A to converge to K, we know that there exists an eventually function that corresponds to the sequence A. So this is some function m, which for every positive real number gives you an integer, that's our eventually number, such that if you have some positive real number epsilon, and if you go past, let me use a little m there, if you go past the eventually number for epsilon, okay, so the output of this function m, so you go that far out in the sequence, then the difference between all of the terms in the sequence A, which are past the eventually number, and this proposed limit k is less than epsilon. All right, so that's just the definition, right? This follows right from the definition of sequence convergence, in this case A converging to K. So similarly, we can write down, right, almost the exact same thing for B, right? So similarly, there exists an eventually function for B. So we'll just call that N. Again, it goes from our domain of closeness, right? How close we need to get to our limit L. And it goes out to our codomain of eventually, right? This is an integer, tells us how far we need to go in the sequence in order to get close. So such that, and again, if epsilon is some positive real number, and now we'll use a little n, is bigger than the eventually number for epsilon, but now using this function n, then the difference between Bn and L will be less than epsilon. All right, so once again, this is just stating a definition, right? This is what it means for the sequence B to converge to L. Now, in order to prove our claim, namely that the sum sequence, right, where you add up the corresponding terms, converges to K plus L, then we're going to need to define a function such that blah, blah, blah. Now, we're going to make one little amendment at the very end, which you'll see that it'll use our Inspired Choice Theorem, all right, which I'll put a link to in the description to our proof of the Inspired Choice Theorem. But let's see what we're going to need to do. So we're going to define now a function. And, well, I don't know, what are we going to call this? How about we'll call it, how about max mn? What a name for a function, right? Why are we going to call it max mn? Well, because that's basically what it's going to do. So this is going to be a function. Again, starts from our domain of closeness and goes to our codomain of eventually. And if you give some epsilon, so some positive real number, what is it going to spit out? I want it to spit out, well, I want to go out far enough so that both of my sequences, right, the A sequence and the B sequence, are going to be within epsilon, right? A with an epsilon of K and B with an epsilon of L. So the way I can make sure that I've gone out far enough, right, is I say, well, okay, for A, I have to go past M of epsilon. For B, I need to go past N of epsilon. Well, one of those is probably bigger than the other, so I'll just go out past the biggest one. So I'm just going to go out past the max value of M of epsilon and N of epsilon. Okay, so whichever one is bigger, I go out past that. Okay, so now the question is, how far away are terms in our sequence, which is now a sum, going to be from k plus L. So let's say I go out far enough. So let's say P is some number. Actually, let's start with an epsilon. So if I take some epsilon greater than 0, and if P goes past my eventually number, okay, so I go past max mn of epsilon, which is the max of m of epsilon and n of epsilon. If I go out this far, then I want to know how far away the pth term of my sum sequence, which is AP plus BP, how far away this is from K plus L. And of course, in the end, I would like to show that it's less than, well, almost epsilon. I'm actually going to, again, use the Inspired Choice Theorem and show that it's less than some constant K times epsilon. All right, well, maybe I'll choose a different letter than K. So the first thing I'm going to do is rearrange what's going on inside the absolute values. I want to put together the AP and the K because I know those are related, right, by what we have up at the top. And then I'll put together the BP and the L. All right, now I have the absolute value of a sum, and so I can actually use the triangle inequality. That's a useful one, triangle inequality. And when I use that, I can break this up as a sum of the two absolute values, AP minus K and BP minus L. Now, because I have gone past m of epsilon, right, the eventually number, right, corresponding to epsilon for the sequence A, once I go past m of epsilon, I know that all the terms in my A sequence are within epsilon of K. In particular, AP has to be within epsilon of K. So I know now that this is going to be less, this first piece is less than epsilon. Similarly, since I've gone past n of epsilon, I know that all the terms in my sequence for B are now within epsilon of L. And so this difference will be less than epsilon. Of course, epsilon plus epsilon is equal to 2 epsilon. Now, this doesn't match the definition for sequence convergence. However, this does match the Inspired Choice Theorem. Right? It says if we can show that there is some constant, in this case the constant is 2, such that if we go out far enough, the sequence terms will be within that constant times epsilon of the proposed limit, K plus L, then we get convergence anyways. So by the Inspired Choice Theorem, the sum of the two sequences does converge to L. Now, typically, in the textbooks, for example, they're not going to use this Inspired Choice Theorem, right? What they're going to do is go back in time and say, instead of choosing my epsilon to go to the max of m of epsilon and n of epsilon, they're instead going to say, well, okay, let me replace m of epsilon with m of epsilon over 2. Okay, so I'll do this on the side here, right? So you could instead go to m of epsilon over 2 and n of epsilon over 2. All right, that's the inspired choice, because now when you get down to the bottom, you would be saying less than, well, now you go out past these eventually numbers, so these differences will be less than epsilon over 2 and epsilon over 2, and when you sum those, you'll get epsilon. All right. So that's how they go back and do an inspired choice. Of course, they don't go through it and then go back and do it again when they print it. That's just how they did it originally. The draft they do, they just start by saying, oh, let it be this, and you go, how did you know to do that? All right, and of course it's because they're hiding, right, all the scaffolding, all the work they did. So instead, we'll just use our inspired choice theorem to say, we know we could make an inspired choice, but we don't want to.